Good day to respected judges, chairperson and fellow participants. My name is Sharon and I am from the Faculty of Pharmacy and Health Sciences, University Kuala Lumpur Royal College of Medicine, Perak. Today, I will be presenting our research titled Formulation and Evaluation of Chitosan Films Incorporated with Banana Peel Extracts. This research was conducted with the support of my final year project student from UniKL RCMP. I would like to acknowledge Ms. Noorfara Nadira for her valuable contributions to this study. For today's presentation, I will begin with the introduction, followed by the methodology, the results and discussion, and finally the conclusion. Let us begin with the background of this study. Plastic packaging is widely used because it is inexpensive, lightweight, and durable. However, the extensive use of conventional plastics has created major environmental problems due to their poor biodegradability. Besides environmental pollution, chemicals from plastic packaging may migrate into packaged products, potentially exposing consumers to harmful substances. Therefore, there is an increasing demand for biodegradable packaging materials that are environmentally friendly and safe. Among the available biopolymers, chitosan has attracted considerable attention because it is biodegradable, renewable, exhibits low toxicity, and possesses excellent film-forming and barrier properties. These characteristics make chitosan an attractive candidate for a sustainable packaging material. Although chitosan has good properties, its functionality can be further enhanced by incorporating natural bioactive compounds. In this study, we selected banana peels because they are an abundant agricultural byproduct that is often discarded as waste. Interestingly, banana peels contain various phytochemicals, including phenolic compounds and flavonoids, which exhibit antioxidant activity. By incorporating banana peel extracts into chitosan films, we hope to produce active packaging materials capable of protecting packaged products against oxidative damage while reducing agricultural waste. This approach contributes to both waste valorization and sustainable packaging development. In this study, pisang awak and pisang emas were selected to compare the influence of banana variants on film properties. Despite increasing interest in biodegradable packaging, conventional plastic packaging remains widely used. Many plastics contain additives that may migrate into packaged products and raise potential health concerns. Hence, there is a need to develop environmentally friendly, active packaging materials that are safe and biodegradable. This forms the basis of our study. The objectives of this research were, first, to prepare chitosan-based films incorporated with banana peel extracts. Second, to determine the physical properties of the films. Third, to evaluate the chemical properties of the formulated films. This research promotes the utilization of agricultural waste as a value-added material. The developed films may serve as sustainable alternatives to petroleum-based plastics while supporting the United Nations Sustainable Development Goals, particularly SDG 3 on good health and well-being and SDG 12 on responsible consumption and production. Next, I will briefly describe the methodology used in this study. Banana peels from two variants, namely pisang emas and pisang awak, were first dried, ground into fine powder, and extracted using methanol by maceration for 5 days. The extracts were concentrated using a rotary evaporator. Subsequently, the chitosan films were prepared by solvent casting before being dried at 27 degrees Celsius for 24 hours. In this study, 6 formulations were prepared. The control formulations contained either PVA or glycerol as plasticizers without banana peel extract. The remaining formulations incorporated either pisang emas or pisang awak extracts together with one of the two plasticizers. This experimental design enables us to compare both the effect of banana variant and the influence of plasticizer on film performance. The prepared films, including the control films, underwent comprehensive characterization. For the physical properties, moisture content, water vapor transmission rate, opacity, and mechanical strength were evaluated. The moisture content was determined by recording the initial weight of the films, followed by drying them in an oven for 24 hours. The final weight of the films was then recorded. The water vapor transmission rate, or WVTR, was determined using anhydrous calcium chloride by measuring its initial weight and the weight after 2 days of exposure to the environment. The opacity of the films was measured using an ultraviolet visible spectrophotometer. The mechanical properties of the films were evaluated using an electromechanical testing machine. The chemical characterization included ATR-FTIR spectroscopy, thermogravimetric analysis, and antioxidant activity using the DPPH radical scavenging assay. Ascorbic acid was used as the standard during the antioxidant activity analysis. These characterization techniques allowed us to determine whether the incorporation of banana peel extracts improved the functional properties of the formulated films. Next, let's move to the results and discussion section. Let's begin with the moisture content results. Films prepared using PVA generally exhibited lower moisture content than those prepared using glycerol. This is expected because glycerol contains multiple hydroxyl groups, making it highly hydrophilic and increasing water absorption within the film matrix. The incorporation of banana peel extracts slightly reduced the moisture content of the films. This may be attributed to interactions between the bioactive compounds in the banana peel extracts and the hydroxyl and amino groups of the chitosan polymer. Among the extract containing films, those incorporated with pisang emas peel extract exhibited lower moisture content than those containing pisang awak peel extract. Overall, lower moisture content is desirable because it improves storage stability and reduces deterioration during packaging applications. Next, let's look at the water vapor transmission rate or WVTR results. WVTR is an important parameter for packaging materials because it determines the movement of moisture between the packaged product and its surrounding environment. All formulations exhibited relatively low WVTR values regardless of the type of banana peel extract or plasticizer used. This suggests that the chitosan-based films possess satisfactory moisture barrier properties, making them suitable for packaging applications. Why is an opacity study required for film packaging? It is because opacity determines the amount of light that can pass through a packaging film. In general, films with higher opacity allow less light to pass through, providing greater protection against light-induced degradation. In this study, the films containing banana peel extracts and glycerol exhibited transmittance values above 82%, indicating lower opacity than the other formulations. Nevertheless, all formulations exhibited acceptable optical properties, demonstrating their potential for packaging applications. Tensile strength is an important property to be studied because packaging films should withstand external forces during handling and transportation. The thickness of the formulated films range from 0.063 to 0.115 mm. The variation in thickness may be attributed to the presence of phenolic and terpenoid compounds, which promote the formation of a denser polymer network by reducing water retention. Pure chitosan films are generally rigid and have poor flexibility. Therefore, the incorporation of banana peel extracts and plasticizers can influence the mechanical properties of the films. Generally, packaging films should exhibit a tensile strength greater than 3.5 megapascal. Among all formulations, the film containing pisang emas peel extract with PVA exhibited the highest tensile strength of 33.88 megapascal, whereas the formulation containing pisang emas peel extract with glycerol showed the lowest value of 2.70 megapascal. This reduction in tensile strength can be attributed to glycerol disrupting intermolecular hydrogen bonding, resulting in a softer and more flexible film. In addition, elongation at break indicates how much a film can stretch before breaking. The formulation containing PVA and pisang emas peel extract exhibited the highest elongation at break, indicating greater flexibility. Overall, PVA improved the mechanical strength of the films, whereas glycerol enhanced their flexibility. The thermal stability of the films was evaluated using thermogravimetric analysis. The PVA-based films exhibited two main stages of weight loss. The maximum polymer decomposition temperature for pure chitosan was approximately 240 degrees Celsius, whereas the PVA-based films decomposed at around 340 degrees Celsius, indicating stronger interactions between the polymer, plasticizer, and banana peel extracts. The onset decomposition temperature of the PVA extract containing films was approximately 188 degrees Celsius. In contrast, the glycerol-based films exhibited three stages of weight loss. Similar to the PVA-based films, the final decomposition stage began at approximately 352 degrees Celsius. However, the onset decomposition temperature was lower at around 140 degrees Celsius. Overall, the incorporation of banana peel extracts into the PVA-based films improved their thermal stability, suggesting better resistance to elevated temperatures during packaging processes. ATR-FTIR analysis confirmed the interaction among chitosan, the plasticizers, and the banana peel extracts. A prominent absorption band at approximately wave number 3270, corresponding to the OH and NH functional groups of chitosan, was more intense in the glycerol-based films, whereas a lower intensity was observed in the PVA-based films. The peak at the wave number 1376 observed in all of the films represents the OH bending present in alcohol, phenol, and carboxylic acid. Furthermore, the peak at wave number 1551 observed in all of the films represents the strong interaction between the amine groups of the chitosan molecule and the phenolics found in banana peel extracts. These characteristic absorption bands indicated that the bioactive compounds from the banana peel extracts were successfully incorporated into the polymer matrix. These interactions likely contributed to the improved properties of the formulated films. Finally, the antioxidant activity of the films was evaluated using the DPPH radical scavenging assay. The incorporation of banana peel extracts markedly enhanced the radical scavenging activity of the films. Among all formulations, the film containing pisang emas peel extract and glycerol achieved the highest radical scavenging activity of 93.99%. This suggests that the pisang emas peel extract possesses stronger antioxidant activity than the pisang awak peel extract. These findings indicate that the antioxidant compounds from the banana peel extracts were successfully incorporated into the chitosan films, demonstrating their potential for active packaging applications. Finally, I will conclude the presentation. Overall, incorporating banana peel extracts successfully enhance the physical, mechanical, thermal, and antioxidant properties of chitosan-based films. Among the 2 banana variants investigated, pisang emas generally demonstrated superior performance, particularly in antioxidant activity. This study demonstrates the potential of agricultural waste as a valuable resource for developing sustainable and functional packaging materials. Future work may include antimicrobial testing and shelf life evaluation under real packaging conditions. The following references were used in this presentation. I would like to acknowledge BITK Mara for funding this research through the Dana Penyelidikan dan Inovasi Mara, as well as UniKL RCMP for providing the facilities and support throughout this project. I would also like to acknowledge the organizer of VCCA for providing a prestigious platform for us to present our research work. With that, thank you very much for your attention.